So here we're going to start talking about Newton's third law. This is our third and final law. And basically for this one, the way it is written is that for every action, there is an equal and opposite reaction. And if you think about what this word action means here in terms of physics, it basically means force. So you could say for every force, there is an equal and opposite force. For every force, there's an equal and opposite force. And what I mean by that is any force that's ever applied, there has to be some sort of counter force to it. And now, so for example, I don't know, if you push a chair, the chair pushes back on you with the same force. If you're standing on the ground and pushing down on the ground with your weight, then the ground is pushing back up on you with a force to hold you up. Okay? So for every force, there's an equal and opposite force. And what we mean by this is the force of A on B is equal to the negative of the force of B on A. So we can even do something like the Earth and the Sun. Here's Earth, here's the Sun, and we know that the Sun pulls on Earth a good amount, makes it go in a big circle, right? So this is the force of the Sun on Earth. But Earth applies the exact same force back, just in the opposite direction. I'm not going to put a negative sign because I put the arrow pointer in there. This is Earth on Sun. If I put a negative sign there, my arrow's pointed here, then it's like a double negative. So I don't put the negative sign there. I took care of it with this arrow direction. But it's the force of the Sun on Earth and the Earth on the Sun, and they're the same, just in opposite directions. So how is that possible? Why? How can the Earth apply the same force back to the Sun? Well, one, it's the law. It's what is observed, so it's not like this is something explaining why it always does. But I guess the confusing part tends to be how is it possible that Earth has the same force on the Sun, yet Earth goes in a big, huge circle around the Sun, and the Sun doesn't move? Well, the Sun does move. It wobbles just a little bit. And in fact, that little bit of wobbling is what they look for to find planets around other stars, because they make the stars wobble. But the star doesn't move nearly as much as the planet, because if you think back to the second law, F equals ma, think about what happens. We have the same force, but on one of these, we have a little mass, so little mass of a planet, giant acceleration. But for a star, it's a giant mass and a little acceleration. And they turn out to be the same thing, because it could be, say, a mass of 2 kilograms with an acceleration of 10 meters per second. That's a force of 20 newtons. But we could flip-flop it. It could be a mass of 10 kilograms, in which case it would only have an acceleration of 2 meters per second squared. It still adds up to the, still multiplies up and gives you the 20 newtons of force. So the same force applied on two different objects gives you a totally different acceleration, thanks to the second law. And we can have the exact same and opposite force on two different objects and them not have the same motion, have very different, wild, different motions here. These opposite, equal and opposite forces are called force pairs, and they always exist. And they're really easy if you just think about them to come up with. If I say it's the force of the bat on the baseball, the pair to that is the force of the baseball on the bat. So it's force of bat on baseball, right? And then its force pair, the one that pairs with it, is the force of the baseball on the bat, right? So no matter what happens, this is what it is. So I guess maybe, you run up and you push something, whatever force you push it with, it pushes back on you with. And so then this brings us to the little thing I was talking about, something sitting on the ground or being pushed against an object. So let's cover this real quick right here. in addition to our force pairs, because this goes along with the force pairs, it's called a normal force. Okay? A normal force. And a normal force is the force of a surface. So the force of a surface on an object. And I'm not sure if y'all are familiar with the term normal from math or anything like that, but basically this means perpendicular. So it's the force of a surface on an object, and it's always perpendicular. I'll use the perpendicular symbol. It's always perpendicular to the surface. So when I said earlier, if you're standing on the ground, right, here's the ground, you're standing on the ground, and you're standing here, the force, you're being pulled down by gravity. And the only reason you're not falling is because your feet are on the ground, right? And the ground is actually applying a force back up on you. So you're applying a force downward on the ground, your weight, mg, mass times gravity for you, right? The acceleration of gravity times your mass, that's called your weight. Okay, that's your weight, the force of gravity on you. And then the ground has to apply an upward force to counteract this, and we call it your normal force. Sometimes it's a script n, sometimes it's an F sub n, just depends on what book you're in, but it's this normal force. It's the force of this surface on you. If you were standing on a hill, right, then gravity would still pull straight down on you, mg, and the normal force then would still be, it has to be perpendicular to the surface. So this normal force would be at an angle to mg. They wouldn't be in a straight line like this. And then you could imagine maybe one other thing, like say you took a book and you pushed it up against the wall and you put your hand on it and you pushed in with your hand this way, right? And you didn't actually, you're not actually taking and holding the book up, but you're just pushing it straight on the wall. Well, then the wall pushes back on the book perpendicular to the book, right, this way. And that would be your normal force. So this would be the force of you pushing it, and then the normal force would push back out, and it would be that force on it. So this is what a normal force is. Get used to the idea, get comfortable with it, and that'll help a lot. But it helps a lot in force pairs. So the force of you on the ground is equal and opposite to the force of the ground on you. And so this normal force can often be a force pair with some other equal and opposite force. All right, so that's pretty much it for the third law.